the point of today is we're going to define trigonometric functions and manipulate them. So once you find a sine, you can find a cosine and things of that sort. So we're going to start with this standard triangle. And this triangle, you can see, is a right triangle. That's what the little square stands for, that it's a right angle there. And that we know that every triangle has 180 degrees sum of all the angles. And so if we have theta and 90 degrees, we know that that angle that's up on top of the triangle up here, that angle is going to be 180 minus 90 minus theta, which is 90 minus theta. So by knowing this one angle, I know what that opposite angle is, okay, with a right triangle. So similar triangles, that means any right triangle that has theta now as its angle down here, we're going to have corresponding angles that are equal, and we're going to have the ratios of the sides are going to be equal. So what I mean by that is that, so for any right triangle that has this angle theta, we know that A divided by C or B divided by C or A over B, any ratio of two of these sides are going to be a particular function of theta. So if you tell me what theta is in a right triangle, all of these other ratios are determined regardless of the size of the triangle. And this is going to be the key to the usefulness of our trigonometric functions, in that it really doesn't matter what size triangle you're talking about. These ratios of the sides are determined by the angle and by the angle only.
Is theta always the two long sides? I don't know.
No, theta is just an arbitrary angle, just like I use x. I'm going to put theta in this triangle. We use Greek letters typically to indicate angles, and so you'll see, you might want to look through your text. I think he does describe a handful of angles. Alpha, beta, gamma, theta, phi, rho, nu, all these Greek letters. I couldn't recite the Greek alphabet in order if you asked me, but I do know what they're called. Okay, so we'll take this triangle, and I'm going to rename them from A, B, and C. I'm going to call this the hypotenuse, the opposite, and the adjacent sides to my angle theta. Okay, so theta is the initial side is the adjacent, the terminal side is the hypotenuse, and then the line that connects the hypotenuse and the adjacent is going to be the opposite. And so you'll see this quite commonly. You probably saw it, or you may have seen it in a high school text or so. It's a really common three-letter abbreviation for these. Okay, so the sine. Now, you spell the sine as a word, S-I-N-E, but we use sine as just this three-letter abbreviation, and we're going to define that as the opposite over the hypotenuse. So for any right angle that we have, if we take the ratio of that opposite side and the hypotenuse, it's going to be the same thing. It's going to be the sine of theta. Now, the sine of theta is not what we call an elementary function. It's a transcendental function. And what I mean by that, a transcendental function, is that it doesn't have any simple algebraic equivalent. It doesn't have a formula like, x squared plus 2x plus 1. It's not made up of elementary functions. It's a function. It's a very particular defined function, and there's ways of calculating it, but it doesn't have a nice tidy equivalent expression that we can use for sine. Okay, then we have cosine. Cosine is the adjacent over the hypotenuse, and then we have tangent, which is the opposite over the adjacent. Okay, so if I go back and I say if my opposite is y and my adjacent is x and my hypotenuse is r, then I'm going to be looking at these ratios as the sine is y over r, the cosine is x over r, and the tangent is y over x. Just an alternate labeling of the triangle. So whenever you think of sine, think of it's that opposite. It's in that y direction is the value that we're interested in, divided by the radius or the hypotenuse. So if we solve, or if we just rearrange these, we can take r sine of theta equals y, and r cosine theta equals x. Now that's, I can also do something similar with a tangent. I would say x tangent theta equals y. And I'll just talk very briefly about a really easy application of this. This is just that last formula, y equals x tangent theta. This really happened to me. I was working in a production facility, and we had a beam up here, and we wanted to know what's the height of this beam. All right, I was in a meeting, and somebody was arguing about it. It's 26 feet. No, it's 32 feet. It's all that. So I said, wait a minute. So I went out there, and I took my little protractor, and I laid on the ground out here, and then I saw, what is this angle here? So I measured that angle, and then I measured the distance from directly below here. So this is my x value, and this is theta. And on my way back, out of breath, I was calculating x tangent theta, and I got 26. So I marched into the meeting, and I said, it's 26 feet. How do you know that? Oh, you measured it. Did you climb up there? No. And I drew that on the board, and that's that. Okay, so you can measure the height of anything by measuring this angle and this distance. Okay? Okay, so the Pythagorean identity here. Remember, y squared plus x squared equals r squared. So labeling my three sides as x, y, and r. If I take this sum of the sons of the squaws on the other two sides equals the sum, no. Anyway, you get this y squared plus x squared equals r squared. And so I'm going to take these, and I'm going to substitute that value for y was r sine theta, and x was r cosine theta, equals r squared. And so I'm going to work it out, so I apply that squared to both the r and the sine and the cosine, and then divide through by r squared, and I get this sine squared plus cosine squared theta equals 1. This is one of the most fundamental trigonometric identities there is. Okay, so this is just one of these identities. At the end, if we get to the end, I'll tell you what you have to know, what you have to memorize. This is one of them. Okay, so just a little side note. Now, when you say the sine squared theta, we're really talking about squaring theta rather than squaring the sine. If we want to have the sine squared, we write the squared right after the sine, and what we really mean is take the sine of theta and then square the whole thing. Okay, so this distinction is pretty important here. And so this probably doesn't exactly follow the order of operations, you know, where we have functions before exponents, but just by convention, this is the way it's always written, and this is the way it's intended to, the intended meaning. Okay, so I'm now still talking about angles that are acute angles, less than 90 degrees. So if we have the sine of theta equals 3/5, what does the cosine equal? No.
1 minus 3/5.
No. Okay, it's going to be, if I set up a triangle, and notice this was, yeah, we have the opposite over the hypotenuse. So I'm going to draw a triangle. It's a right triangle with the height of 3 and a hypotenuse of 4. I can use my Pythagorean theorem and come up with the adjacent equals 4, and so the cosine equals 4/5. Now, remember the sine squared and cosine squared equals 1. So if I take 3/5 squared plus 4/5 squared equals 1, here I get 9/25 plus 16/25 equals 1, and I got 25 over 25. So that works. And in fact, you didn't need to even draw this unless you wanted to. I think it's pretty easy to visualize what's going on when you do it this way. You calculate what that side is, so you know you have a 3, 4, 5 triangle, and then go back to your definition of cosine and say, oh yeah, it's the adjacent over the hypotenuse. You can also use that sine squared, cosine squared thing by realizing that you have 3/5 squared plus the cosine squared of theta equals 1, and so the cosine squared of theta equals 1 minus 9/25, and so we find the cosine squared of theta equals 16/25. Take the square root of both sides, and you get the cosine of theta equals 4/5. That's the other way to do it.
So that's just a check to make sure you get it right?
Yeah, it's either checking or calculating. I mean, this is a perfectly good way to calculate the cosine. Now, occasionally you get really goofy numbers, you know, but ultimately all the calculations are the same. Notice it involves the numbers 3, 4, 5, 9, 16, and 25. And however you arrange those, you have 3 different strategies of calculating the one that you're missing. Okay. So you try this. All these, the angles are going to be less than 90. And I'll talk later about what happens when the angle is greater than 90. So I want you to find the other 2 functions that I'm talking about, given that first the sine of theta equals 5/13, and then the cosine equals 1/2, and then the tangent of theta equals 1. So find sine and cosine. So I'm giving you one. So this is 3 separate problems. These 3 don't relate to each other. I just want you to do 3 of them.
What does this sign and everything correspond to? Like, which one corresponds with X?
All right, so this first one, I'm going to draw my reference triangle, and I notice that a 5, 12, 13 triangle is a right triangle, so I can calculate 13 squared minus 5 squared equals 12 squared. And so then the cosine is going to be the adjacent over the hypotenuse. The tangent is going to be the opposite over the adjacent. Okay, so I laid out my triangle. And the nice part about it, when you have a ratio, a nice clean ratio like this, you can always lay out your triangles with integers. And remember, the radius doesn't always have to be 1. It can be 1. But since you have a ratio, why not start with your triangle with a hypotenuse of 13 opposite of 5? It's a right triangle, so you take 13 squared minus 5 squared equals 12 squared. The 5, 12, 13 triangle is like a 3, 4, 5 triangle. You see it a lot. So you know, you might want to keep that one in mind as one that you know and don't have to calculate. Okay, so this next one. So I'm going to draw my triangle, and my hypotenuse is 2, the base or the adjacent is 1, and so if I take 2 squared minus 1 squared and take the square root of that, I get the square root of 3. So here I have my 3 ratio, or here I have my 3 sides, and so the sine is going to be the square root of 3 over 2, and the tangent is going to be the square root of 3 over 1, or just plain old square root of 3. Yes?
But this way, like, now you're just doing it with the Pythagorean theorem. This other way, you were doing it like it was supposed to equal 1. Like, I thought that's what we were trying to
Sine
learn.
squared plus cosine squared equals 1 is the Pythagorean theorem.
But it's like different. Now you're doing just the Pythagorean theorem.
Okay. If you like to do it that way,
What I don't, but I thought
then
that's
what you can do is do this. Okay? And so you know 1 squared minus 1/2 squared square root will equal 3/2. Okay? Here you're just dealing with more fractions. And so here I'm taking advantage of the fact that I have a ratio, so I can keep integers, and chances are I'll just end up with a radical or a radical over 2 in the worst case. Same thing with this one. If the tangent is 1, that means the opposite and the adjacents are equal, so make them the easiest equal that you can make is 1. So the hypotenuse is the square root of 2. And so we get the sine of theta is 1 over the square root of 2. And if we rationalize that, it's the square root of 2 over 2. And we get the cosine of the square root of 2 over 2. Okay, we'll continue this on Wednesday. Please read your textbook. Okay, it'll make this a lot easier, and we'll be able to scoot along a little bit more quickly.